Hi everyone, today I want to talk about my project, Transportation Network Analysis. First, I want to introduce some background information about transportation network. In order to connect cities, like this picture, we have to build the road. Our project consider how to lower the cost and shorter the road to build the road connect to cities. And we simplify the problems as the topology of a network. We analyze how to use the simply and the cheapest way to fulfill that topology, like this one. We use Dijkstra algorithm to fulfill the shortest route, and the minimum spanning tree algorithm to fulfill the lowest cost. These two are our major problem. Now, first I want to talk about the connectivity. Connectivity typically means the degree of connectedness within a transportation network. The high connectivity means the low isolation and high accessibility. Low connectivity means high isolation and low accessibility. These two are just in contrary. And if we location are connected directly, we code with A1, else we will code with A0. Then we need to reduce the transportation network to matrix format with only A1 and A0. We assume that the distance as topology distance only one, and number the vertices and create a matrix. Here's a matrix. We will code direct connection as one, and we use just this half of the arrow first, and copy this half of the matrix to the upper this arrow, and we finish it. Now we power the matrix to determine two steps linkage. We add the two matrices, and the matrix now represents all 1 and 2 step routes. This new matrix is then powered again, and the whole process is repeated. Finally, we will powering and adding procedures again and again until all 0 cells are filled. Like here is a 0 cell. And the result shows that the least accessible node is 7 with 40 connections. This one, node 7. And the most accessible node is node 1 with 224 connections. This one. And now I want to talk about the minimum spanning tree. There are 3 major properties of minimum spanning tree. The first one, possibility, multiplicity. And the second one, uniqueness and the cut property. Sometimes we will get more than one minimum spanning tree. The 2 trees on the right shows 2 different possibility of minimum spanning trees of this given graph. And here is a description of the Dijkstra algorithm. Dijkstra's algorithm can find the shortest path between 2 different places, like this A1 to AB, A1 to B3. We pick the vertex with lowest distance, compute the distance, find to another neighbor. If it is similar, we update its distance. Now we'll show you our program and show the results. And I use Python to write the program. First, I want to show you my minimum spanning tree program. Here is a list of my program. You can see it. Now I will show you the result to run this program. Now it's running, and we're back to our PPT. We try to minimize spanning tree algorithm to solve the problem, and we will code up prime minimum spanning tree algorithm. We use the text file describe an undirected graph with integer age. For example, the third line of the file 23 minus 8,874, just indicating that there is an edge connecting vertex 2 and vertex 3 that has cost minus 8,874. And if you just change the one is cost is minus, we do not assume the edge cost are positive. It can be minus, can be negative, and we will test to run prime minimum spanning tree algorithm on this graph. We will report the overall cost of a minimum spanning tree an integer, which will be, both can be positive or negative. And this graph is small enough that the straightforward time implementation of Prime's algorithm should work fine. And for those seeking an additional challenge, we try to implement a heap-based version. The simpler approach, which should already give us a healthy speedup to maintain relevant edge in a heap. Now I will show you my result. Here's the result by using minimum spanning tree. The purpose of this program, like I said, is to choose some parts of the route to lower the cost. Age 379 and 378 here, cost 2,951 means that this point and this point, if you want to connect them, you have to pay this price. Yes, it's minus. And finally, we can go to the total minimum cost to connect all the network, to build all the necessary connections. That is the final price, this one. And now I will show you my Check-Straw algorithm. I use this to build the shortest pace. Here is my document writing programs here. Now I try to run the programs here. Now it's running, and I will back to my PPT. Here's my program, you can see, and my input data. And we will use program to code up thickest tree shortest pace algorithm. We use the file contains an adjacent list representation of indirect weight graph with 200 vertices labeled from 1 to 200. Each row consists of nodes that are adjacent to that particular vertex along with the length of that edge. For example, we talk about the 6th row here. The next entry of the row is 141. Indicates that there is an edge between vertex 6 and vertex 141 that the length is 8,200. The rest of the pairs of this row indicates the other vertex adjacent to vertex 6 and the length of that corresponding edges. We will test to run Dijkstra's shortest pace algorithm, and I already showed you that on this graph, using a source vertex and to compute the shortest pace distance between one and every other vertex of the graph. If there is no pace between a vertex V and vertex 1, we will define the shortest pace distance between 1 and vertex V to be 1 million. And you can see here, we will report the shortest pace distance to the whole distance. We will encode distance as a comma-separated string of integer, and we will report, all the shortest connection. Here's the result. Like I said, the purpose of this program is to choose the shortest pace. Maybe some shortest pace. And here's the result. Shows the shortest pace for every 2.21. For example, here 22, 132, 25, 143, 198, 145, 1, and 4028 just simply means that if point 1 need to be connected to point 22, It should be step by step connect to 145, 108, 143, 25, 132. This is the shortest way. The point 1 can connect to point 22, and the distance, the shortest distance, required distance is 4022. Now we can do the summary and conclusion. I use the two major algorithms to analyze the transportation network and fulfill two major problems. My purpose. And simply, I use the minimum spanning tree algorithm. We need consider the cost to connect to cities, to lower the cost, and we use Dijkstra's algorithm when we care about the length of the path mostly. We choose the shortest way to connect one point to another point. And thanks for your listening. Thank you.